Okay, so we are a couple of minutes past the hour. So thank you everyone for coming to this week's Flash Talk. It's the last Flash Talk of the semester. And today we're pleased to have Dave Coulter, who is a grad student at UCSC working with Ryan Foley. And I think usually he works on type 1A supernovae, and he's going to be talking to us about the R process gold rush today. So when you're ready, Dave.
Okay, yeah, thanks for the introduction. I'm happy to be here, happy to talk about the origin of the heavy elements and specifically the R process. And since this is a short talk, I want to get right into it. I'll have a little intro here. We'll talk about the R process, about kilonovae, how we search the discovery of the first optical counterpart to a gravitational wave source, a couple interesting objects in O3 that have implications for the R process enrichment, and what we're looking forward to in the next observing run. Okay, so first to contextualize the R process, I'd like to go through some basics, and I'll start with beta decay, which is quite simply how neutrons stop becoming neutrons by decaying into charged particles. And beta decay features heavily in the S process. S here stands for slow, and by slow we mean that the time scale to obtain another neutron for the nucleus is slower than the time scale of beta decay. So, the consequence of this is that as a nucleus is taking on neutrons, it will quickly decay to stability if it's unstable, and you hew close to this valley of beta stability. What that means, though, is that there are heavy isotopes that are inaccessible to this kind of nucleosynthetic path. And to get there, you need something like the R process. R here stands for rapid. So this is where the inequality is flipped, and the time scale to obtain a neutron is very quick compared to the beta decay time scale, which lets you build up very heavy isotopes quickly and then decay into these heavier elements. YE, or the electron fraction of a material, is essentially a way to quantify neutron richness. So if you have equal numbers of protons and neutrons, that's a YE of a half. Versus if you had 4 times as many neutrons as protons, that would be a YE of a fifth. And it turns out that because we need so many neutrons for the R process, you really need a YE of less than a third to make that process go. However, these neutrons themselves can be destroyed. So inverse beta decay is the process by which neutrinos, either being emitted from something hot or some other kind of physical process, can actually denature the neutrons and frustrate the R process and prevent heavy element production. So we know that gold is an R process element, and we know the alchemists of yore tried to make gold through a variety of means, but now we actually have a recipe to make gold. All you need is lots of neutrons, incredible densities and temperatures, but the upshot is you only need about a second. So a natural astrophysical site where these could happen are kilonovae, because neutron stars, they're made of lots of neutrons, and when they merge, they produce these conditions. So I wanted to go through an anatomy of a neutron star merger. If 2 neutron stars merge, there should be some tidally disrupted material, that this ejecta, that can be neutron rich, but in this case, if it wasn't a direct collapse to a black hole, that surface of the neutron star could provide neutrinos, thereby raising that electron fraction. However, if you have a particularly massive system, or if you have a neutron star black hole merger, the final remnant would be a black hole, and you would expect the electron fraction of that material to be quite a bit lower. Now, once the R process has gone and you've synthesized a lot of these heavy isotopes, there will be a decay process that powers a radioactive transient that's more or less isotropic, called a kilonova. So that's really what I'm going to focus on in this talk. But there also happens to be these mechanisms to produce non-thermal radiation, like short gamma ray burst or circumburst interactions. Okay. So kilonovae are radioactively powered, and we know how to understand radioactively powered transients like type 1A supernovae. We know that we need a heating rate. We need to know the opacity as well as the ejecta mass and velocity. And there are strong predictions for heavy elements, R process elements like lanthanides, when it comes to these quantities of interest. So the heating rate, you can see here in this plot from Roberts, all these gray lines are really an ensemble of different lanthanides with different half-lives that in aggregate have a heating rate that goes as T to the minus 1.3. So it's a strong prediction. Lanthanides also have incredibly high opacities. So in this next plot, you're seeing wavelength versus opacity, and the blue and the teal are iron group elements whose opacity declines pretty rapidly as you get into the mid-infrared, where lanthanides, the green and the red curves, remain fairly opaque. And the consequence of this is the behavior of these light curves. So this is brightness versus time. And for something that had a very low lanthanide fraction or lanthanide free, you have very fast evolution of that light curve. So the light can escape, it's going to be blue, and you infer that that's going to have a high YE versus something like a kilonova that it's going to be polluted with lots of lanthanides and take longer to evolve. So with this framework in mind, we can think about this question: are neutron star mergers the dominant sites of the R process? So one advantage to asking this question is that neutron star mergers are compact object mergers, and those things are loud in gravitational waves. And it just so happens that we have a whole network of gravitational wave detectors. Depicted here on the left is LIGO Hanford, in the middle LIGO Livingston, and then on the right Virgo. And these detectors basically detect time of flight differences in gravitational waves. And by doing that, we can localize a gravitational wave on the sky. But that also complicates the picture because these localizations, which is what you're seeing here on the sky, can be hundreds or thousands of square degrees. And when you're trying to find an optical counterpart to one of these gravitational wave sources, it's like looking for a needle in a haystack, but you're looking through a straw, right? And so one way to address this is to burn down the haystack. And we can do that essentially by, oh, excuse me, this was just a metaphor here for saying that the field of view of the full moon is a quarter square degree shrunk down to this scale, you wouldn't see it, right? So one way that we can make progress in this is to use a galaxy catalog to target galaxies, and that's because compact object remnants come from stars, and stars live in galaxies, and galaxies cluster. So if we can take advantage of that, then we don't have to essentially mow the lawn and just try to cover the entire localization region. And so to do that, you need a catalog. And so we're going to use the GLADE catalog. And I've essentially built this into a software tool called Teglon that I have put together, which essentially creates a moving grid of equal volume cells as a function of distance. And we can calculate the enclosed B-band luminosity in each one of these volume elements and divide it by what we expect to be there to get a local spatially varying catalog completeness. And using that catalog completeness, we can inform how we search. Now, once we have a geospatially enabled database, we can have other value-added data like dust information that helps us plan observations. And I want to go through sort of the algorithm that we use for prioritizing what we look for. So this is the canonical galaxy ranking system. So we care about if you're closer to the center of the highest probability region in the localization map, which is what these blue curves represent, we would want to prioritize those galaxies. And given the same contour, galaxies that are in the right 3D position, as opposed to being a gigaparsec away from where LIGO thinks this event happened, we'll prioritize those. We also prioritize the brighter galaxies because they have more stars. We can do one step better because that galaxy targeting approach really works well if you know where all the galaxies are, but it's possible that these events happen so far away that our catalog completeness is very low. So what I wanted to do was in Teglon interpolate between this galaxy targeting approach and this sort of tiling approach of just sort of covering as large of a fraction of the probability as possible. And so the way we do that is, say if we're 50% complete, I want to take 50% of the probability in the LIGO sky map, distribute it amongst the galaxies in this way, and then leave the rest in the field. And then I can use queries against the database to pick the best targets, right? And so this is a simulation of that, where the red squares say we have 20 observations and we want to know where to point the telescope. As we take this event and move it into space, our catalog completeness is decreasing. And what you'll see is that we recover the strategy of purely just tiling the inner 50th percentile, as opposed to when we're very close, we're going to pick these galaxies. So Teglon allows us to have this interpolating kind of strategy. But of course, you might not find an actual counterpart. So how do you calculate an upper limit? We can do that with Teglin as well. These LIGO maps are broken into pixels, and each pixel has values like distance prior, where they think the merger happened, as well as a probability. But we can marry that with a family of models with the line of sight dust, and take all the covering observations that have covered that pixel into account and calculate essentially a distance modulus that lets us understand how far away can we see this model, and then combined with the pixel properties and summing over all pixels that are covered, we can get a detection efficiency for a family of models. Right. So to do this kind of work, you need tools to go look for these events. And so for O2 and into O3 and beyond, two of our biggest tools that we use are the Nickel telescope at Lick Observatory in California and the Swope telescope in Chile. And there's obvious advantages to having telescopes in both hemispheres. You get full sky coverage and you get redundancy if there's any weather effects, if the transient is between them. And I think at this point, it's pretty clear in 2017 what happened. There was a neutron star merger detected by LIGO. There was a coincident gamma ray burst, and we know those can be a part of these kilonovae from what we covered before. And at the time in 2017, my advisor Ryan Foley and I were in Copenhagen at a gravitational wave meeting. And so this is a little bit of a spicy text, but I'd like to include it as a part of the historical record, because he went on vacation, he went on a date with his girlfriend, and we get the email from LIGO that there's this neutron star merger. And so here I am as like a first year grad student trying to text him that he needs to come back and we need to find this thing. And long story short, I finally did convince him, but he came back and then we started looking. So I'm going to show you here what our search program was. This was at 43 megaparsecs, so we were reasonably complete. So we were targeting galaxies. But the additional optimization that we did here is we didn't just target galaxies with single pointings, we clustered those galaxies and pointings so that eventually when we did image the first optical counterpart to a gravitational wave source, it was on our 9th image. And here's that image. This is the galaxy NGC 4993. You can see helpfully put with the red arrow from the data reduction step, that's where the kilonova is. And just to prove that it wasn't there before, this is a pretty serendipitous HST imaging just a few months prior. Okay, so what powered SSS-17A, which is what we called it and since been called AT 2017 GFO. You can see here the first observation taken 11 hours after merger. It's fairly blue, but 4 days later, it decreases in brightness considerably and becomes red. So we can take those light curves, we can fit these kilonova models. And Charlie Kilpatrick did this fantastic paper where he basically showed that you need more than one component. You need more than one mass, more than one opacity to really explain the full bolometric light curve. So you need some early lanthanide-free blue component, which was surprising that that would be a part of this kilonova, as well as what you'd expect, this low YE, high lanthanide component. Okay, so then we can go back to this fundamental question about galactic enrichment. If you look at the rate given by LIGO in the Milky Way and the yield, and then similarly look at the mass fraction of the R process in the galaxy, you find that these are roughly equal. So to first order, yes, neutron star mergers can account for the R process budget, at least in the galaxy and the local universe. But the story is complicated by the fact that we don't exactly know, all the ways that kilonova can be, right? We didn't know that there could be this blue component or what even that blue component was. So this is work from Yair Kavi, who is showing these light curves with different fits for different models, so that the solid lines are radioactively powered transients, lanthanide-free transients, versus some kind of shock cooling. And the takeaway for this is that we didn't get an image of the kilonova until almost 12 hours after merger. And if we really want to distinguish between these models and therefore understand the contribution to the light R process, we need to have basically earlier imaging. Okay, so this launched, this really supercharged this multi-messenger astrophysics field. There was lots of work done in everything from the speed of gravity to the physics of short gamma ray burst, the R process that we're talking about today. And it really whet our appetite to continue engaging with these, with the observation campaigns of LIGO, looking for these counterparts. And so in O3, I want to talk about this particular object, GW 190814. This was a neutron star black hole merger, we thought at the time. And what was exciting was it was a very small area, so we thought it was a very tractable problem. But also, interestingly enough, the secondary mass was 2.6 solar masses, which is quite small, or I'm sorry, quite big, right? It's either the largest neutron star ever detected in gravitational waves or the smallest black hole. So this will have implications for the R process. Here's our search footprint. We used Teglon to pick these fields, but you can see it's such a small area that we didn't really need that. We could just literally plaster it with observations, but what Teglon lets us do is combine all of these limits agnostically, right? And then there was many candidates that were all essentially disqualified for various reasons as not being related. So because of that, we can calculate upper limits then. And so the natural thing to do is to take the components, the blue component of the kilonova, the red component of the kilonova, and see if we're sensitive to those. And in this case, you can see not so great. And that makes sense because at 260 megaparsecs, this is, you know, more than 5 times as distant as the kilonova. So while we didn't have a very good, you know, ability to constrain a blue and a red component like AT 2017 GFO, and you can see here the story gets worse for a red component because they're intrinsically fainter and slower evolving. We have pretty strong constraints on whether or not there was a gamma ray burst that was pointed at us. And we have pretty good constraints as well if that gamma ray burst was up to like 17 degrees off, just like the gamma ray burst associated with the kilonova. Okay, and so I want to make one point here that even if this was, you know, 2.6 solar mass is probably a black hole, but even if it was a neutron star, it was unlikely to produce ejecta that would have been visible. Here on the horizontal axis, we have the mass of a black hole, so the primary, versus its spin on the x-axis. And these curves here, corresponding to neutron stars of different masses, show where we would expect disruption. So when you go to the upper left-hand corner of this plot, we would expect there to be some material that was disrupted outside the innermost stable orbit or the event horizon of the black hole. And if we put GW 190814 up here, essentially, you have a black hole that's off the chart and a neutron star that's very massive. It's very unlikely that that would have produced ejecta that you'd see. But looking at the other neutron star black hole merger candidates in O3, all of them are in tension like this, and they all require substantial spins of the primary to be able to make out any ejecta. So, and it's important to note that all of these black holes had spins consistent with 0. So the last object I want to talk about is 190425. This was the second ever neutron star merger detected in gravitational waves. And what was really interesting about this was the total mass of the system. Now, when you compare this to the population of double neutron star systems you see in the galaxy, it's quite a bit different. And so we think that because this is, safely in excess of the maximum mass of a neutron star, that we would have had a direct collapse to a black hole from these 2 neutron stars. This is the localization region as visualized by Teglon, which is quite vast, right? So this was essentially a 1 detector event by LIGO Livingston, which meant that the localization was on the order of 10,000 square degrees or a quarter of the sky. But this is actually where Teglon shines, because at this distance, we have roughly about, in aggregate, 50% catalog completeness. And when we convolve that with the localization map, and then essentially redistribute that probability to the galaxies that we know about, it really increases the ability for small field of view telescopes to sort of search efficiently. And here's another view of the localization regions with observations from the literature overplotted, because I was able to load these into Teglon, like I was mentioning before, it's agnostic. And again, just pointing out the fact that, you know, for a very large field of view like ZTF, you know, redistributing the probability to galaxies as opposed to leaving in the field isn't going to have as big of an effect as it does for a small field of view telescope like the Swope or like Swift. Okay, and we can play the same game where we're looking at the calculated limits, and we do much better here because this event happened much closer than 0814. Okay, so we have a reasonably, you know, greater than 10% chance. We're really limited. This 30% maximum probability is really a product of how much of that localization area we covered. But the red component is still very challenging. Again, we have very good constraints on gamma ray bursts that are beamed towards us, as well as slightly offset. Okay, so we can do a little bit more than that. We can combine electromagnetic information with gravitational wave information. In particular, we know that neutron stars have to have some relatively slow finite spin, that neutron stars must be more massive, or at least the maximum mass of the neutron star must be more massive than the most massive pulsars we see in the galaxy. And by doing that, we can sort of shrink this M1 versus M2 parameter space that LIGO puts out. They put out this sort of agnostic just properties that they measure from the gravitational waves, but using our priors that we have from astronomy, we can actually shrink this down. And like I mentioned earlier, this was likely to produce a very red, low YE ejecta, which would have been very, very dim. So while we were tuning our observations for something like 0817 at 160 megaparsecs, really, we should have been optimized for something redder and fainter, because you can see here the limits are almost 4 mag dimmer, so almost a factor of 100 more faint. So this is information that LIGO doesn't in real time give us, but would be really great to help with our follow-up. Okay, and looking forward to 04, there's just going to be a lot of events. So we're really excited for the amount of neutron star mergers that could be detected, neutron star black hole mergers as well. And we have a lot of resources to bear on this problem. In fact, I've put in a cycle 30 HST proposal to follow things in the optical in case they're sort of detected at ground threshold. And we also have an accepted JWST proposal, which will be critical to follow these things in the mid-infrared and be able to get data that could actually definitively show that our process elements are being created, possibly even actinides, which we would expect to have late time effects on the light curve, as well as being able to detect these chemical fingerprints in the spectra. So to close, kilonovae do synthesize lanthanides. We saw that from fitting the light curves of SSS17A, but the diversity of kilonovae do complicate this this calculation, this average calculation that I did. Search strategies still matter, and this is evidenced by the fact that if we had early time observations of the blue component, we could have ruled out certain models. And there is this aspect of just the red kilonovae, either from a neutron star black hole merger or high mass binary neutron star mergers that probably should contribute almost exclusively low YE material. 04 is going to be wild, and hopefully JWST helps us balance the R process budget of the universe. So thank you, and I will pause now and take questions. I'll leave my takeaways up.
Okay, great. Thanks, Dave. That's really very exciting work. I can see we already have a question. So Ben, go for it.
Hi, thank you for a great talk. I remember hearing years ago that, long before all of this, that a lot of people had rejected the hypothesis of neutron star mergers forming the R process because the merger time would be longer than the Hubble time. Clearly, that's not the case. So why, what changed in, and is it now accepted that, gravitational wave driven mergers can happen much, much more quickly than we thought? So, what changed in the intervening years?
I think things have changed both. I'm not an expert in actual the channels that lead up to these kind of mergers, but I can say that I have friends that work in common envelope evolution. So there's a lot of theoretical work that can show how you can shrink this semi-major axis with these compact objects, and therefore sort of start out in ways where you can merge within a Hubble time. So I think there's a lot of work being done there, as well as exploring dynamical ways of forming these things where you don't have to start and from a large separation and somehow close that gap within the age of the universe. But I would say also, we just didn't know until we had data. And so with LIGO running, they can calculate these volumetric rates and get better senses of what the actual statistics are. So I think as LIGO progresses and continues to take data and theoretical work is continuing to be done, we'll close the gap between that sort of expectation that we would never see this to, we're expecting maybe a dozen events seen in gravitational waves, at least, starting this winter.
So I had a quick question. So I think on the figure you showed for, is it 80 GFO or whatever the number is, where you had the models and you had like the combined model.
Yeah.
It looked to me from that figure like it's still like underestimating what you actually see. I'm just wondering what kind of component would bring it up to make a better match there at later times.
Right. Sorry, I'm trying to get to what I think you're talking about this one here, the bolometric light curve.
I think it was, yeah, that one.
Right. Well, so these are pretty large error bars too, because by 10 days, the kilonova was almost non-detectable, right? So I think part of this is just that's where JWST is going to come in, right? JWST is going to be able to follow these to fainter limits, to redder wavelengths, which we didn't have with AT 2017 GFO. Also, behind the scenes, because things would look like they were asymptoting to like 2000 degrees at the photosphere, which is like roughly the recombination temperature of the lanthanized open F shells. It's more like all of these things came together to sort of paint this picture that it was a red component that was powered by lanthanides. But really, I mean, there's different ways to fit this. This is a two model or a two sort of component model that was fit to this, but there's been work by a lot of other people, like Ashley Villar's excellent work on it, fit a 3-component model where there was like a purple component that driven by a disk. And so, there's also a lot more. I didn't have time to talk about all the complications. There are viewing angle effects that can change the color. You might be seeing more polar ejecta versus not. So I think that there are a lot of degrees of freedom right now for how you can fit these things. And so, given just 2 components to fit, I think this is why you're probably seeing some divergence. It's true though that in the light curves were pretty well fit, but the spectra were not.
Right.
Yeah. So having a better understanding of the SED as it goes redder is going to really help the modelers.
Okay, cool. Yeah, I see what you're saying. Okay, are there any other questions for Dave? I guess not. So I guess we'll say thank you to Dave again.
Yeah.
Hope everyone has a great bank holiday weekend. And this was the last Flash Talk. So yeah, it's done for the year. Have a nice summer.
Okay. Thank you very much.
Bye.
Bye-bye.